So now let's continue, guys. Let's make a geometry and make a planar. I will leave it as it is, but I will reduce this number. As we can see here, maybe reduce it a little more, something like that. Then I will make a Vellum constraint class, configure class, then Vellum solver. For now, everything is the usual. Let's make if space 3 for the side, I think, and let's select all those like this. Hit enter. Now they are in the pin. Now they pinned. Okay, and let's make a test for a big head. Make a shadow like this. I will scale it like that, maybe. Okay, I'll make it 0.3. Yeah. And at first, let's make it at the Z, maybe like this. We'll put a keyframe, then 24. Make it forward like this. Keyframe, then back to 0 again. I will leave it as is, no problem. Okay, I will use it as a collision, and let's see the simulation. Okay, as we can see here, we are facing some problems like this. This notch should supposed to act this way. So we have first a problem in the collision itself. Okay, it's not occurred. So what we should do is to increase the collision passes to maybe 50. Let's see now how it's gonna be. Of course it will be much slower, but it will give us a much better result. So when we face a problem in the collision, that's what we should do. Of course this one should be this was okay, 0.6. Make it like this. Last keyframe, I'll make it like that because it should go back to its original place again. Okay, so back to our topic. Now let's test the plasticity. Let's see what plasticity do. Stretch enable plasticity. As we can see here, we have a new panel called plasticity opened. Okay, let's see first if I hit play, see what's happening. Okay, so let's check what's happening. Not sure. Okay, yeah, as we can see here, it leaves something like it changed the shape, and somehow it leave it like this. Okay, this meaning it make a new receipt lens, right? So it's becoming more like cellophane or plastic. This is what plasticity for. The new after the stretching, it doesn't go back to its original receipt lens. It freeze. Like this is a new receipt lens for it. So let's see the parameters that we have here. First we have a threshold. Okay, determine of course the percentage of the plasticity flow, how much plasticity would we will have. Okay, let's see what we have here. Below this, the material will return to its original shape when deformed past the threshold. It will begin to creep into its new configuration. Okay, so after the stretching, if the threshold across this percentage, it will remain for the new receipt lens. It will not going to stretch back, right? I think this is the percentage of the stretch, and we here called pica ratio. Okay, the threshold can either be absolute distant or be percentage distant. Yeah, so we have absolute distant or percentage distant. A value of 0.1 as a ratio. This ratio they mean would mean stretching of 120 and 110% of compression of 90 will triggered plastic flow. This means if we have 0.1, meaning 0.1, this called stretching 110 and compression of 90. This means it will follow. To be honest, it's a little confusing. Okay, but this is a percentage between this number and the compression stiffness because of the ratio. If we uncheck it, that means we are totally depend on this distant, and this is a distant. This is a distant where the stretching stretch distant of the stretch. Okay, meaning if we have 0.1, meaning if this shape or planar stretch to 0.1, anything after 0.1 or 0.1 will freeze, will not back to its original shape again. Okay, because 0.1 is a big distance. So maybe if we make it 0.1, let's see what's going to happen. Yeah, so as we can see here, some of it remain the same. Plus, if we even reduce this number more, we will have more plasticity, right? Let me see. Yeah, so as we can see here, it become much more. And also we can check from the stretch plasticity flow. If we put here, of course, 0.01, it will show us exactly what's going on. As we can see, all this is stretching and all this will remain for its new receipt lens or new stretching. It will not going to back to its original distance again. It will remain for the new lens or the receipt lens. Okay, so let's continue. Maybe I will make the ratio. Also for the rate itself, the speed at which the material adapts its new receipt lens when it began to flow. Yeah, so technically this is a speed. As much as we put number here, as much as we will have more plasticity, less number here just mean we will less much plasticity than it usual, because we don't have enough time to have to the plasticity to take over, right? Yeah, I think this number is very small. make it like this maybe. Okay, so let's see what we have here. So basically we don't have much for the plasticity because I increase this number, so of course it will not going to catch more plasticity, and also for the ratio. But let's say if we put here 5 for example, let's see what's going to happen. So as you can see here, we have more plasticity take over, as we can see here when we increase this number. So if we make it 10, let's see. So this is basically a speed determine the plasticity flow, okay, separated by this separated from this number. So let's make another geometry. Inside it, let's make another planet patch, and let's make it horizontal like this, and maybe here I will make it 0.3, so we have enough polygons. Then I will put a scale here, a keyframe in the scale, and I will maybe make it 4, maybe 5, and then it will back again to 1. Perfect. Let's add a Vellum configure class. First of all, I don't want to see the show guide. Second, I want to have those 2 rows of point inherit the position, the original position of the point, okay, because here it will just simply fall. Of course we need a Vellum solver first. Vellum solver. So if you play it like this, it will fall. We don't want that. We want to have a pin to animation space 2. Let's add those 2 both line or rows. Enter. Yeah, and match to animation. When we do match animation, it will inherit the original position of each point of those. So it will, all this pin points, it will move to with the original only, but at the other point it wouldn't. So the class or the Vellum constraint will take over all over the points except those 2 rows, okay. Now let's see what we got here, what we should do. Yeah, what we should do, we have a plasticity. Let's check it. No, this is not a plasticity, this is a plasticity. Okay, so now let's talk more about hardening. Okay, so let's see what we have here so far. It's stretch. Oh my god, it's stretch. Yeah, and remain the receipt length change. So let's go to the Vellum solver. Let's choose stretch plastic flow just to see what's happening. Okay, next let's start to play a little with the plasticity, especially the hardening, to understand what the hardening for. As we can see here, it doesn't have the stiffness is full. Okay, plasticity will take over like this. Let's see if we increase this number like hardening. Let's see if we make it like 10, what will happen. Yeah, well, actually nothing much happened, but let's increase this number and see again. Okay, so as we can see here, there is something happening, something goes on. It suddenly stopped because the hardening here, this is the 10, that's mean here if we make it more, let's make it 1, this is different. Yeah, as we can see here, it take much longer to be hardening. It's more like losing energy or getting cold from hot. Yeah, let's say, as we can see here, it's getting hot faster, right? So I think basically this is what hardening mean. Yeah. Yeah, so as we can see, it's keep going down, but keep going down, I think, from the because of the stiffness itself. Okay, but in general, you can play with it, find yourself, have some description. Yeah.